Right, I hope you found the exercise okay. Let's go through this exercise with the 11-step method. Now don't forget, step 1 is the design objectives. Now in this case, the design objectives are not for life safety, but for property protection only. They want you to ensure that the smoke layer is maintained at least 0.5 metres above the stock in the building, and this will give a clear layer height of 10.1 metres. That's step 1. In step 2, you need to determine the design fire size, and this obviously is going to be used in all your calculations. And this obviously is the worst case scenario. Now this has been given to you, it's been identified as 4 metres by 4 metres with a heat release rate of 875 kilowatts per metre squared. This is the formula you needed to apply. QP equals Chi times AS times QF, where your QP is your convective heat output, Chi is the convective portion of heat output, AS is the area of the fire, and QF is the heat release density. If you put those variables in, you get 0.67, which is the default for Chi if not expressed otherwise, times by your area, which is 16, times by 875, the convective heat output is 9380 kilowatts. So that's step 2, working out that. You know the design fire size. Let's move on to the next step. Now step 3 is determining the mass flow rate of smoke. You know your size fire, how much smoke is that going to give off? Well, first of all, you've got to establish whether it's classified as a simple or a complex plume. Well, in this case, we know the design fire is actually located in the reservoir where it's going to be extracted, so it's a simple plume. So that's the model for a simple plume. Then you've got to decide which model of simple plume. Is it a line plume? Is it a corner plume? Wall plume or an axisymmetric plume? Well, because we don't know, it could be anywhere, the stores could be in there, you must assume it's an axisymmetric plume, and the reason is this will give you the greatest mass flow rate. So therefore, in this case, we're going to use an axisymmetric simple plume. Now, next thing you have to do, don't forget, is to work out whether it's a near field model or a far field model. If the clear layer height is greater than the longest dimension of the source, the longest dimension of fire, multiplied by 5, then it's deemed to be a far field model. If not, it's a near field model. Well, in this case, 5 times the longest dimension, which is 4 metres, you know the size of the fire, is 20. And the clear layer height is 10.1. Clearly, this is classified as a near field model. And if it's a near field axisymmetric plume, this is the formula you have to apply. M equals CEP times Z to the 1.5, where M is the mass flow rate in kilograms a second, CE is the coefficient of entrainment, P is the perimeter of the source, and Z is the clear layer height in metres. Now, don't forget, in this one, you've got to establish the coefficient. There's different coefficients depending on the clear layer height. Now, if the clear layer height is greater, this time more than 3 times the longest dimension, then you have to use 0.19 as your coefficient, and if it's not, you apply 0.21. Well, in this case, 3 times 4 is 12. Clearly, this is still greater than the clear layer height of 10.1, and therefore you apply 0.21 as your coefficient. This is what you've been trying to work out, which model or which coefficient. Put these into your model, and it gives you 0.21 times the P, which is 4 plus 4 plus 4 plus 4. That's the perimeter, which is 16, times 10.1 to the power of 1.5, gives you a mass flow rate of 107.85 kilograms a second. That is what you've had to work out. That fire size with that smoke layer will give you 107 kilograms per second mass flow rate. We know how much smoke is going to produce. Now, how hot is that smoke going to be? Let's move on to step 4. Step 4 is determining the temperature of the smoke. Now, to determine the temperature of the smoke, you use the following formula. Theta equals QP divided by MC, where theta is the increase in temperature. Your QP, don't forget, is your convective heat output. M is your mass flow rate, and C is your specific heat capacity of the smoke. You put in the known variables in the formula, you get this. Theta equals 9380 divided by 107.85 times 1.01, which is the specific heat capacity of the smoke, gives you a theta value of 86K. So in other words, that smoke will be 86 degrees above the ambient. That's how much energy that smoke's got. That gives you the average. Now, I would like to point out that obviously this 86 is well above what we classify as the stagnation temperature. Anything less than 20 degrees K, you're not going to get the buoyancy, so you can't use natural vents. Well, that's well above this. We know the temperature increase, but how hot is the smoke? Well, you use this formula to work out the temperature of the smoke. TL equals TO plus theta. Your TL is your absolute average temperature, which is what you're trying to work out. TO is the ambient temperature, which is generally considered to be 288, and your theta is your temperature increase. Put this out, it gives you a temperature of the smoke layer of 374 degrees Kelvin. So that's how hot it is. So now you know how much smoke we've got and how hot it is. We now need to start determining how you're going to extract that from that building. Before we're determining this, you just have to at least consider stratification, the phenomenon called stratification. Now, in tall buildings, this is significant. Now, in this building, it's only got a clear layer height of 10.1 metres. You're not going to get stratification in this building. You're generally looking about 20 odd metres. Anything under that, you're not going to look at. So stratification in this case is not a problem. Right, let's move on to step 6, determining the ventilation requirements. Now you've got a couple of choices, haven't you, really? You can either go for natural ventilation or mechanical ventilation. Now, generally, natural ventilation is preferred mainly due to the cost implications. And if it's possible, they want natural ventilation. But there are limitations when you can use it and when you can't, and I'll cover that later on as we go through the example. Now, in warehouses, you'd normally apply natural ventilation if possible. So let's progress on the assumption that natural ventilation is to be used in this case. Now, the first thing to determine is the number of reservoirs that you're going to have. So that's the first thing you should do when you decide on natural or mechanical, how many reservoirs are you going to have. Now, for cost reasons, again, normally people try and have the minimum number of reservoirs that you can. So you don't want loads of reservoirs, you try and get the minimum you can as long as it achieves the design objectives. Now, there are limits to the size, the maximum size you can have for a reservoir. Well, generally, smoke reservoirs are limited to between 1,000 and 3,000 square metres, depending on the circumstances. And this is to ensure that there is no significant loss of heat. In other words, the smoke will be extracted. Now, the general limit is 2,000 square metres if it's got natural ventilation, and it's 2,600 square metres if it's got mechanical extraction. Now, however, if the primary objective is not for life safety, but primary for property protection, then the size of the reservoir, whether it's natural or mechanical, can be increased to 3,000 square metres. So if it's purely for life safety, then it's 2,000 and 2,600. If it's for property protection, no life safety implications, you can increase it to 3,000 square metres. And this applies to nearly all types of occupancies. However, in the UK, we have amended these reservoir sizes for shopping malls. So you've got to remember, if it's a shopping mall, there's different sizes. In a shopping mall, smoke from shop units is generally limited to 1,000 square metres in plan area, and this can enter an area with a reservoir with a maximum size of 1,000 square metres. Now, both of these can be increased to 1,300 square metres for mechanical. So what they've done is they've halved the values. Now, another common limit that you've got to make sure you've got to apply with is the maximum length limit. This, no dimension should be more than 60 metres, which is measured along the midline of the reservoir. So it can't be more than 60 metres long. Now, as we mentioned in the course, this limit comes from a UK committee which identified that people should not have to travel more than 30 metres to get out of a reservoir. And this is based on psychological reactions of members of the public in such circumstances. And this generally sticks, whatever the occupancy, 60 metres will generally be the longest dimension you can actually apply. So they are the general rules in determining how large your reservoirs can be. Now, in this example, it's for property protection. That's the design objective. So you can have a reservoir up to 3,000 square metres. So let's look at our warehouse. Now, as you can see, this has got two separate spans, which are 40 metres wide. Now, the length is 140 metres. Now, because the maximum size reservoir is 3,000 square metres, but you've also got the 60 metre rule. It can't be more than 60 metres in one dimension. Yeah, because you see now, because it's 140 metres, you could argue, well, halfway through 170 metres. Well, you can't have it 70 metres. So in this case, you would have to divide it by 3, which would give you 47 metres. So this is the size of the reservoir. You would have 6 reservoirs, 47 by 40 metres. That's what you would have in this situation. We know that. Now we need to determine the area of ventilation required to extract the amount of smoke that's been produced in each reservoir. So we know how many reservoirs, but in each reservoir, what area of ventilation is required to get all the smoke out that we calculated earlier. And this is termed the AVCV, where AV obviously is the geometric area and CV is the coefficient for that particular type of ventilator. Like I said, we normally express it as AVCV because we're not sure what coefficient we're going to use. By specifying that, the designer will then just look at the coefficient and then they'd specify what size ventilators. So what formula do you use to work out the AVCV? Where your M is your mass flow rate, rho 0 is your density of ambient air, which is normally taken as 1.2. Your TL is your absolute temperature of the smoke layer. Your AVCV divided by ACI is your ratio of inlets to outlets. Now, in this case, because we've got 6 reservoirs, you're only going to get a fine in one. You've got 1 outlet, so you've got 1 lot going out, but you've got 5 potential inlets. So in this case, that ratio would be 1 divided by 5. That's your ratio. Then you've got your TO, which is your ambient air, which is 288. Your gravity, 9.81. We know the depth of the smoke layer and we know the theta. We put them in. You should have put them in this formula. This is what you should have got. And if you multiply that out, you should have got an AVCV of 26.087 square metre. That is the aerodynamic free air. That's the aerodynamic free air. Now that covers this step. So we've worked out what the aerodynamic, the AVCV is. Let's move on to step 7, which is determining the number of ventilators. So how many ventilators do we need to achieve this? Well, we know the total area of ventilation is 26.087, but that's the aerodynamic free area. In other words, you've got to take out how efficient the area of the ventilators are. Now, generally, the coefficient for ventilators is 0.6. That's generally. So if you divide it by 0.6, you understand we need at least 43.47 metres squared of geometric area of reservoirs, ventilators in that reservoir. So now we need to consider how big ventilators are. Well, ventilators themselves don't come any bigger than 6.25 metres. And that's because they can't test them. That's the biggest they can get in the test rig. So you're not going to get ventilators bigger than 6.25. Now, if you divide it out, 43.47 by 6.25, you know at the very least, you need at least 6.96 or 7 ventilators. So you're going to have at least 7 in that area. That's the minimum. Now, where do we locate these ventilators? Let's look at where we locate them now. Well, before you decide this, you've got to carry out the stagnation check, which is step 8. This only applies to natural, but we are going for natural. And what it says is, ventilators can be no more, the maximum distance from the edge of a building to a ventilator is 10 metres, and they can't be more than 20 metres apart. This is because in natural ventilation, they'll stagnate. The smoke will stagnate, it won't make it across. It'll stay in the middle, it'll stagnate. So in natural ventilators, you have to apply this. So what do you do with these figures? Well, you put these in your reservoir. Let's look at our reservoir. We've got our reservoir, each one is 47 metres by 40. And you mark a line at 10 metre and 20 metre intervals. So you mark where you're going to have at least some ventilators. Yeah? So in this case, as you can see here, we needed 7 to meet the requirement of area. But based on this now, we need at least 8 ventilators. Can you see on there? We need at least 8 ventilators located as we have there. And those 8 ventilators must have a minimum area of 43.47. So there must be at least 5.3 square metres each. So that is what they've got to be geometrically. Now that covers step 8. So we know now how many ventilators we are and how big they're going to be. Now we need to move on to step 9. You've got to carry out the plug holing check. You've got to make sure that the smoke will not plug hole and cause a vortex which will induce air and affect the efficiency. Now you do this for both natural and mechanical ventilation. Now again, don't forget there's two models which determine if plug holing is likely to happen, and it depends where the ventilator is. If the ventilator is less than 2 metres away from the edge of a wall, you use one model, and if it isn't, you use the second model. Well, in this case, it's not within 2 metres, we use the second model, which is this one here, this M-Crit. Where the M-Crit obviously is the maximum flow that can go out of there, the maximum mass flow rate without plug holing. You've got rho zero, which is your ambient density. You've got your acceleration due to gravity. Ambient temperature. We've got the theta in there, which is the increase in temperature. D is your smoke layer depth. And don't forget, you've got your WV factor, which is the width of a circle with the same geometric area as your ventilator. You've got to convert your square, whatever it is, whatever shape it is, into a circle to insert in this formula. And to do that, you use this formula here, where WV equals the square root of 4 times your geometric area, make sure that's your geometric, per vent divided by pi. Putting that in, you get WV is equal to 2.63. So that's the width of a ventilator circle that would match the same dimensions as your ventilator, 2.63. Now you've got all your variables, put them in the M-Crit formula. Once you put all them in, you get an M-Crit of 68.37 kilograms, which is very high. This critical is quite high. And what that means is each ventilator, if it's extracting more than 68.37 kilograms a second, if it's extracting more than that, it's likely to plug hole. Well, in this case, our total mass flow rate of all the smoke in that reservoir is 107.85. If you divide that out by your 8, which you've got 8 different ventilators, can you see you're only going to get approximately 13.48? Well, that is clearly much lower than the M-Crit. In other words, you are confident that plug holing is not likely to occur. And that covers that particular step. No plug holing. Step 10 is to check the air inlet velocity if necessary. Well, that does not apply in natural ventilators, and we've also got plenty of air inlet coming from the other reservoirs, so you don't need to carry it out. That's more for when you've got mechanical ventilation and especially in a life safety role. So again, step 10, in this particular case, you can miss. The final check you need to carry out is step 11, which is the post-design considerations. And in this case, you would ensure that weather conditions would not have an adverse effect on ventilation and that the pitch of the roof is not greater than 30 degrees. In other words, you've got to look through the wind criteria, you've got to look at your curtain, you make sure your curtains are not going to deflect, and you've got to look at tall buildings in that area. They're the sort of things I would expect you to look at in the post-design considerations in step 11. And that completes this exercise.